The next gate we shall discuss is the inverter or NOT gate. This is very similar to the buffer gate in that it only has one single input and one single output, but the outcomes are completely different. The logic gate stipulates that when the input is 0, then the output is 1. It also states that when the input is 1, the output is 0. Let's construct a schematic diagram showing such a gate. This will consist of a single transistor, an LED, switch, a battery, and two limiting resistors. When we connect the battery, current flows from the positive through R1 to the switch, which is currently in its off state. Current then continues through R2 and through the LED and back to the battery, which causes the LED to light. We could say that in this example, when the input is 0, then the output is 1, since the LED lights. Before we continue, let's consider what role our transistor is playing in this circuit. In fact, we shall remove the battery, R1, SW1 and TR1. Now when we connect the battery, the current flows through the limiting resistor R2, through the LED, and an electrical path is made to the negative of the battery and the LED lights. So this gives us the first state. Let's reattach the battery R1, SW1 and TR1 to switch back to our original circuit. This time we shall close the switch. Current flows like before through R1 and R2, but this time the switch is closed and the transistor becomes conductive between the collector and emitter. This reduces the voltage across the LED, so this time the LED does not light. We can test the voltage at this point. This reading is 0.039 of a volt, which is far too low for the LED to light. If we open the switch again, we can see that the voltage is much higher, over 2 volts, and the LED lights. So to conclude our truth table, when the input is 1, the output is 0. An inverter NOT gate reverses a digital signal, turning a high to low and vice versa, which is essential for Boolean logic negation, creating complementary signals, building more complex logic gates like NAND and NOR, and managing general polarity. It is the fundamental blocks, data, inversion and inversion basic logic functions. We shall now create a practical version of this gate. The first item we'll be choosing is the switch. Again, it does not matter at this stage where on the breadboard it is placed, as long as we follow the schematic diagram. Next is R1. This can be found on the left of the switch and connected to the positive rail. The transistor is next. We must bear in mind it is polarity dependent. Reversing it can cause damage. Also, we must keep in mind that the pinouts, emitter, base and collector. We could place the LED direct to the collector of the transistor, but we have chosen to leave some space between them. Then connect them using a link for clarity. R2 is connected to the positive rail and to the positive of the LED. From the right hand side of the switch, we will use a link to the base of the transistor. A further link from the emitter of the transistor to the negative of the LED. We can see from the schematic diagram a link from the collector of the transistor to the positive side of the LED, and one final link between the negative rail to the negative of the LED. Let's reconnect the battery in our schematic diagram. The current flows along the top rail and down through R1, but since the switch is open, cannot flow any further to the base of the transistor. The current continues through R2 and the LED and to the negative of the battery, completing the circuit, and the LED lights. In our practical circuit, we connect the power wires to the breadboard and current flows through the positive top rail. It continues through R1 to the switch, and since this is in its off state, cannot flow any further. Meanwhile, the current continues through R2, then the LED to the negative rail, completing the circuit and the LED lights. At this point we could say that the input is 0 and the output is 1. Let's reset the circuit and close the switch. The current flows through R1 to the base of the transistor, turning it into a conductive state. It also travels through R2, but since the transistor is in its conductive state, the voltage across the LED is not great enough to turn it on. In our practical breadboard, the switch is turned on and the current flows through the top positive rail, down R1 and to the base of the transistor, turning it on and reducing the voltage across the LED so the LED remains off. Therefore, when the input is 1, the output is 0. You will see that this particular gate is commonly used with other gates we have yet to meet.